From massive data to precise logic, today we explore how AI can both learn and reason. Deep learning builds statistical models by adjusting millions of parameters or weights. It shines at vision, speech, and language. Picture a network tuning itself to recognize what a cat looks like in a photo. But when data is scarce or rules matter, black box nets can't explain their choices, can't handle if-then logic, and often fail to generalize. Imagine a neural network getting stumped on a puzzle piece that doesn't match its training data. That's where symbolic AI steps in. Symbolic AI uses human-readable rules, like if it rains, then take an umbrella. It can reason over exceptions, unless it's indoors, and trace how conclusions follow from premises. Now let's dive into the neurosymbolic cycle. First, a neural module processes inputs, images or text, and outputs continuous vectors. Picture layers of a CNN encoding an image. An extractor then turns those vectors into symbolic facts, for example, cat, object 1, sitting, object 1 mat. Imagine vectors morphing into cat x and sits x mat. Next, a logic engine applies rules like spatial relations to answer queries or plan actions. Think of a logic graph expanding, with queries highlighted. Finally, extracted rules feed back, softly constraining further learning so the network respects known logic. Visualize arrows looping back, adjusting a loss curve. There are 6 integration styles. First, neural I/O, where the network handles input and output. Second, solver hybrid. The network feeds into an external solver like a chess engine. Third, modular pipeline. A perception net connects to a logic module. Fourth, compiled knowledge weights stamped with a rule. Fifth, differentiable logic formulas inside a loss function graph. Sixth, in-network reasoning attention heads attending over clauses. These patterns range from loose coupling to full symbolic reasoning inside neural architectures. Let's look at some real-world examples. AlphaGo uses a CNN plus Monte Carlo tree search to play Go. Deep Problem combines neural perception with probabilistic logic, translating an image into symbols and queries. Logic tensor networks use formulas to guide training curves. These methods power game playing, scene understanding, and knowledge-guided learning. The benefits are clear generalization, solving new puzzles without retraining, data efficiency, learning from fewer examples, explainability, tracing decisions with logic proofs, and safe AI, enforcing hard and soft constraints. Imagine applications in robotics, medical imaging, and autonomous vehicles. However, challenges remain. Scaling rule extraction, bridging fuzzy neural inferences with crisp proofs, and designing intuitive human-AI dialogues are active frontiers. Picture a UI where a user queries, "Why did you choose that path?" and the AI shows a proof tree. That's the power of combining learning and logic.